Hello everyone, welcome back to the another session in Design and Analysis of Algorithms. The topic name is Cook's Theorem. This topic you will find in 5th unit as topic number 4. Now let's get started. Before we discuss about Cook's Theorem, let's have a clarity about these 4 terms. We made a video already to discuss in detail about these 4 terms, and we have a single glance to understand what exactly these are to enter into the Cook's theorem. Now, let's assume any problem P. That problem P can be a deterministic problem or it can be a non-deterministic problem. When a problem is said to be deterministic problem, if the problem while it is executing, if it takes polynomial time computing, or the computation time of this P is polynomial time, then we say it is deterministic problem with polynomial time. Or if the problem P is non-deterministic with the exponential time. Even the words of deterministic and non-deterministic we clearly mentioned in the previous video on this topic. Deterministic in the sense what? The algorithm what you are writing for this problem P. Let us suppose that algorithm A is written for problem P. All the steps or algorithm are defined, then it is deterministic. Only few steps or algorithm determined, and there are other steps which are undetermined, then it is non-deterministic algorithm. So, when you wanted to solve a problem, that solving a problem is what? Knowing the complexity. If you wanted to know what is the time it takes to complete the problem, then we will be having two things. What is polynomial time and exponential time? Now, what is P? P is the problem is said to be P when it is a deterministic with the polynomial time. The problem P is said to be non-deterministic when it is non-deterministic with exponential time, right? And these are what? P class, NP class, or else P and NP. Done? Now come down. All non-deterministic algorithms will take exponential time. This is what we were understood. In the last previous video of this, we were made one point clear with the example algorithm that few steps of the algorithm will take polynomial time and the other steps inclusion it takes exponential time. So we divided this NP into two problems, NP hard problem, NP complete problem. NP hard problem, the name itself it says it is hard. That is, you cannot get the solution. Yes, there are problems which we cannot get the solution. All NP complete problems are NP hard. Today you have one problem that is from NP hard. Now tomorrow you are going to solve a problem that is NP hard. So most probably all problems are NP hard problems. We will be solving the NP hard problem step by step and will be differentiating that the problem which are executed in polynomial time, the NP hard problem only, if it takes polynomial time of execution time, we say it is NP complete. If the problem is not it taking polynomial time, if it is not comes to the all the steps are known and something this, then we will be saying it is NP hard problem. So NP hard problem still it is in research, and that's what every day there will be an upcoming technology, upcoming topic where we will be seeing a solution towards of many problems. So every problem is what? NP. NP is a superset. When you have a superset, this superset is going to have everything. Now from everything we'll be taking one by one to out to solve it. Then it becomes P, right? So this is what the beauty of P, NP, NP hard, NP complete. If you can understand this particular slide with these 4 terms, you can rule Cook's theorem. It's on your fingertips to understand. Now let's see what is Cook's theorem. So Cook's theorem is basically introduced by Stephen Arthur Cook and Levin. So these are two persons who introduced this Cook's theorem. So it is also known as Cook-Levin theorem. Cook's theorem is seen. It is introduced in 1971. So Cook's theorem basically takes Boolean values, that is true or false values, and it is what satisfiability problem. Now, what do you mean by Cook's theorem? The definition of Cook's theorem is what? It states that satisfiability is in P if and only if P is equal to NP. So in the previous video, we were done about satisfiability problem, what it is. So simply you can say it is SAT problem or satisfiability problem. Satisfiability problem will say that P is always a subset of NP, and Cook's theorem will prove P is equal to NP. So we did not to prove that P is from NP. No. Because just now we discussed that every unknown topic is proven which we taken from NP. So there is no meaning that you say P is from NP. No, you have to say that NP is from P. That's what. Now, so P subset of NP, P is equal to NP. Both are, this is from satisfiability and this is from Cook's theorem. Now, we'll take some example to understand the same. So I told you that NP is a superset. Now let's see, in superset, sorting technique and searching technique is there. In superset, we don't know what techniques we had. So we don't know about linear search, we don't know about binary search, bubble sort, merge sort, all these sorting techniques we don't know. They are in non-deterministic algorithm. They are in this NP set. So when some researchers are coming out with their great implementation, they will be taking one from this NP to P. They are converting or they are finding the solution for these problems, and those are comes to the P. So day by day, when researchers are doing something on these superset problems, P value will grow and it will occupy the whole NP. So one day your all NP problems will be solved. One day all your NP problems will be solved. That means all NP problems one day turned into P. And this is what Cook's theorem. Now what we are going to do is, we'll take some problem and we will be going to solve this problem with the deterministic. Fine. Now we will be knowing one expression. Let's see that I know about ax square plus bx plus c equation. I know. That means this equation, I say that it is polynomial time. Right? It is a deterministic algorithm and it takes a polynomial time. Now what is NP? NP is from this expression you can take any of the expression. So I wanted to calculate some 2x plus 4. Okay. So now this expression may varies from time to time, and I wanted to I can find many things from this equation. I can find multiplication, I can find addition, I can find subtraction with the negative numbers, I can do number of things on this, right? So now NP is what? You will take one of the problem and say that it can be solved into P. So we'll take that example and we'll move now. So I'm taking the example. So here the example is what? I am taking one problem. The problem is what? Q. It is termed with the Q. So for the problem Q, I am writing a algorithm A with the input I1. Here I wrote about Q1 and Q2. Q1 is what? P problem. Q2 is what? NP problem. So what we have to make sure is, you should make sure that your NP problem will get solvable. And if one NP problem, see I told you in the beginning before slide that merge sort is NP set or superset from NP or one problem of NP. Now the day is big, by the time when researchers wanted to solve this merge sort, it became to P. Now today a problem is there that is maybe NP, but one day it will come to P. Every problem will get solved. Now, so Z is a deterministic algorithm. So now I2 is input, M is equal to number of inputs, A is non-deterministic algorithm. That is what the algorithm what I am writing. Now I1 is input, N is number of inputs. Now keep this in mind. Now the proof of this theorem, or else we now prove this important theorem. We have already seen that satisfiability is in NP. Hence, if P is equal to NP, then hence if P is equal to NP, then satisfiability is in NP. Right? I repeat, P is equal to NP, then satisfiability is in P. It remains to be shown that if satisfiability is in P, then P is equal to NP. To do this, we show how to obtain from any polynomial time non-deterministic decision algorithm A and input I. Now that the formula or the solution is what? Q of A comma I, such that Q is a satisfiability SAT problem if and only if A has a successful termination with input I. If the length of I is in N and the time complexity of A is P of N for some polynomial P, then the length of Q is exponential. A deterministic algorithm Z says that outcome of A, algorithm of A, and in any input of I can be easily obtained. Now this algorithm Z simply computes Q and then uses deterministic algorithm for satisfiability problem, and the complexity is what? Q of M. Now if big O of Q of M is the time complexity needed to determine whether a formula of length M is satisfiable, then the complexity of Z is exponential plus, that means big O of P power 3 N log N plus big O of P cube of N log N plus Q of P cube of N log N. If satisfiability is in P, then Q of M. If satisfiability is in P, then Q of M is a polynomial function of M and the complexity of Z becomes polynomial. Hence, if satisfiability is in P, then for every non-deterministic algorithm A in NP, we can obtain a deterministic Z in P. So, the above construction shows that if satisfiability is in P, then P is equal to NP. So, this is what Cook's theorem. We will be proving that one undefined problem or one problem with the few steps are not determined and few are determined, then that few can be defined through the defined algorithm or defined things. So that is what Cook's theorem says. P is equal to NP. Thank you all.